In this online lecture, we're going to look at electronegativity, the dipoles that they cause in bonds, and then at formal charge also. Electronegativity comes from the ability of an atom to pull harder on the bonding electrons than the atom that it's bound to. So if we look at this bond right here, you'll see that the two atoms are the same, and so they're equally sharing these electrons. If I look at this bond, there's a shift in the electrons over toward Y, because Y is more electronegative. And that shift in the electrons towards Y, now this is only the bonding electrons, that shift causes a slight del negative to build up on Y. What is this del right here? This del is the symbol that means partial in math. So it's saying a partial negative. It's not a full negative. It's only a little bit of negative. Because the electrons are being pulled over to Y, there's a small positive charge that builds up on X. And we call the two of these together, the del positive and the del negative, a bond dipole. If the electrons get attracted to Y so greatly that it pulls the bonding electrons completely over onto itself, then there's a full negative on Y and a full positive on X, and we call it an ionic bond. So basically, this is just to emphasize there's a continuum from nonpolar covalent to all the way to ionic, and polar covalent is somewhere in between. Okay, how do you know which is the more electronegative atom? The way that you know what is the more electronegative atom is to look at the trend in the periodic table. As you go up and over in the periodic table, you get more electronegativity. Now there's no bonding with the inert gases on the right-hand side. So the most electronegative element is fluorine, way up in the corner right next to neon. Anything that is closer to fluorine than another is more electronegative. The thing that's farther away is less electronegative. Now, the only one that we have to worry about is hydrogen, because hydrogen is a nonmetal, but it's not over there with the nonmetals. It's on the metal side of the table. Just remember that hydrogen is less electronegative than all the nonmetals except for phosphorus, and it's the same as phosphorus. But we're not going to see too many phosphorus-hydrogen bonds in organic chemistry. All right, just keep in mind that carbon has an electronegativity value of 2.5 and hydrogen is equal to 2.1. You don't need to have these values memorized. Carbon, hydrogen is considered nonpolar, even though there is a difference in electronegativity. Why? Because the electronegativity difference is not large, and when you have carbon-hydrogen bonds, there's usually a lot of symmetry to that part of the molecule, and so the effect of that small dipole is negated by the symmetry. So we just usually consider all carbon-hydrogen bonds to be nonpolar because of those two attributes. The very polar bonds are oxygen-hydrogen, nitrogen-hydrogen, carbon-oxygen, carbon-nitrogen, and carbon-halogen. These are the ones that we focus on in organic chemistry because there's a large dipole with these. Well, here it's not hugely large, but there is a good bit of polarity. And these bonds, because of the large difference in electronegativity, have strong polarity and therefore affect the behavior of the molecule, both in reactions and in physical characteristics. So the polarity of all of those bonds is important to remember. They're polar. The oxygen, the nitrogen, and the halogens all are going to have a del negative on them, and the carbon always has a del positive on it. Hydrogen, when attached to oxygen, nitrogen, or even carbon, we tend to ignore that, but hydrogen, when attached to oxygen or nitrogen, all will have a del positive. So keep in mind, del negative on oxygen, nitrogens, and halogens. Carbon and hydrogen will have del positive. Okay, if we look at induction, the inductive effect is, induction basically means to induce polarity. So the inductive effect is that a polar bond will cause polarity in a nearby bond, or cause the polarity to be even greater. So here's an example right here. The carbon-fluorine bond has a large del negative on the fluorine and a large del positive on the carbon. The oxygen normally has a del negative and a del positive on hydrogen, but because the fluorines are pulling the electrons in this oxygen-hydrogen bond over onto itself, what it does is it causes a greater, it's like the electronegativity of the fluorine is causing the electronegativity of the oxygen to be greater. So what you have is a greater polarity in this bond with a larger del positive than in methanol down here. You can't see it here. Hold on. This oxygen-hydrogen bond has a larger del negative and del positive on the oxygen and hydrogen than the oxygen and hydrogen in this bond. Why? Because the fluorines are so electronegative, they're pulling the electrons in this bond over onto the oxygen, making a larger del positive on the hydrogen, larger del negative on this oxygen. So now I want you to try to draw in the bond dipoles on these bonds. Make sure you put the del positive on the correct atom, del negative on the correct atom where there is a dipole. When you get through, pause, and then when you get through, restart and check your answers. Okay, so on this bond, the carbon is less electronegative than the oxygen, so you get a del positive on the carbon and a del negative on the oxygen. The nitrogen is more electronegative, so the carbon gets a del positive, nitrogen gets a del negative. This bond down here is nonpolar, so there is no dipole. On this bond, the hydrogen is less electronegative, the oxygen more electronegative, del negative and del positive on the hydrogen. The same thing with this nitrogen-hydrogen bond. There ends up being a del positive on the hydrogen, del negative on the nitrogen. And this bond has a del negative on the carbon and a del positive on the hydrogen, but we usually ignore this because symmetry takes away this small dipole, and we usually don't bother writing it at all. All right, so dipole moments. The dipole moment is when you look at a molecule and you look at it, what is the overall dipole in that molecule. So what you have to do is look at both the shape of the molecule and the dipoles that are within that molecule. So if I look over here at water, I know there's a del positive on hydrogen, a del negative on the oxygen, and a del positive on the hydrogen, and the tetrahedral electron geometry makes the molecule bent. As a result, there's positive down here and negative up here. This is actually measured and given a value of 1.85 dynes. And this is a relatively large dipole for a molecule. Now, if we go down to this molecule, you can see down here there is, we don't really look at because they're carbon hydrogens, we don't really look at the polarity of this. So we ignore that and we look up at this part of the molecule. This part of the molecule, the oxygen has a tetrahedral electron geometry, so the molecule itself, at least on the oxygen to hydrogen-oxygen carbon bond, this part of the molecule is bent. There's a del positive here, del negative, and del positive here. That actually makes the dipole point. Positive over here, negative over here. and the measurement is only slightly less than for water. So this is methanol, and it's a very polar compound. If I look at ammonia, del positive's all down here, del negative up here, and so we end up having a del positive on this side of the molecule, negative on this side of the molecule, and the measurement of it overall is pretty good and strong. Notice that where are we getting dipoles? It's when there are non-bonding pairs in there. So if the central atom has a non-bonding pair on it, which oxygens and nitrogens are going to pretty much always have non-bonding pairs unless they're protonated. And if they're protonated, they're going to have charge. So whenever you see oxygen and nitrogen, you're going to have polarity in that area. The non-bonding pairs cause asymmetry, and so that is what causes the dipole to be established. Another thing that can cause a dipole to occur is that you have different groups attached to a central atom. For instance, if you have a carbon with 2 hydrogens and 2 chlorines, what you're going to find is there's going to be a significant dipole in there. Not as great as, let's say, for here, ammonia, but it will still be very detectable. The longer the bonds, the greater the dipole moment. Why? Because longer bonds cause more charge separation. The greater the difference in electronegativity, the greater the dipole moment. We actually see that here with water and ammonia. The electronegativity difference between oxygen and hydrogen is 3.5 to 2.1 versus down here with nitrogen and hydrogen is 3.0 to 2.1. So there's a greater difference in electronegativity up here, so that ends up giving it a greater dipole moment. Okay, where do you see no dipole moment? When you have a symmetrical molecule. What causes a lack of symmetry? What causes symmetry? To have symmetry in a molecule that causes no dipole moment, what you have to have is the groups on either side of the central atom. So this carbon is a central atom, and the oxygen and oxygen are the same, and there are no non-bonding pairs on the central atom. So this molecule will be nonpolar. If I look at this one, all the atoms on the outside are the same, and there's no non-bonding pairs on the central atom, so it's nonpolar. If I look at this, no central atom, this nor this, have no non-bonding pairs. Okay, the atoms on the outside are all the same, so it has no dipole, it's nonpolar. Here's another one. Look at the symmetry around this. Of course, there's no non-bonding pairs, but if I cut this in half this way, the 2 sides are the same. If I cut it in half this way, the 2 sides are the same. And if I turn it on so that it's the hydrogen at the bottom is coming out at you, you would find that it is flat. Trigonoplanar are all of the carbon atoms. And because of that symmetry, the top is no different from the bottom, and you would find that it has no polarity. So all of these molecules are nonpolar. Now, what I want you to do is look at these molecules and using the tools that I've given you, determine which one of these would you expect to have a dipole moment. Pause it and then restart it after you've determined. Okay, if I look at these molecules right off the bat, you can see the non-bonding pairs on the oxygen, the non-bonding pairs on the nitrogen and oxygen, and the non-bonding pairs on the oxygen. Whenever you see oxygen and nitrogen, there's always going to be non-bonding pairs there unless they're a charged species, and charge induces dipole, or it causes a dipole to be there, or polarity to be there. So if I look at these, all 3 of these, you would expect to have a dipole moment, and they do. The only one that does not have non-bonding pairs is this one. And look, the atoms on the outside are all the same. So this is a nonpolar molecule. Okay, so let's go to formal charge. If I look at formal charge, this is not a real charge. Formal charge is a tool for helping us determine where charge might reside. So it's a tool. If I look at DMSO right here, and I take away the positive and the negative, and let's just look at the Lewis dot structure. If I look at the Lewis dot structure, I would find that this oxygen has more electrons on it than you would find on oxygen when it is just an unbound atom. Oxygen has 6 electrons on it when it's an unbound neutral atom. If I look at this, these 2 electrons are being shared in this bond. So we could say that the oxygen has a net of 1 on it. And then it has 3 non-bonding pairs in addition to that. So that would give you a net of 7. 6 electrons on oxygen when it's a neutral atom versus 7 means an extra electron. So formally, there's a -1 charge on the oxygen. Likewise, if we look at the sulfur, sulfur has how many electrons on it formally? There's 1 from each bond, 3, and then the two electrons as a non-bonding pair, 5. Well, sulfur has a valence shell of 6. 5 is 1 less than 6, so that gives sulfur a formal charge of +1. Why is it that we do this? We do this because what we find is there's a lot of negative charge residing on oxygen and a lot of positive charge residing on sulfur. It's not a full positive or negative like you would see in an ionic bond. And because there's 4 areas of electrons around the sulfur, we find it is tetrahedral, and so it gets this shape over here. This is a trigonal pyramidal shape. There's a non-bonding pair sticking out over here that gives the electron geometry tetrahedral. And so this actually is quite representative of what the molecule behaves like. So this goes through the steps in calculating formal charge. Determine the number of electrons that are on it formally, half of the bonding electrons, and all of the non-bonding pairs. Subtract this from the valence number, and that gives you the formal charge. And I already went through this part with you. You can read through it and try to figure it out again after what I did for you. When you get through with the formal charge, we usually write it on the structure. Okay, go ahead and try these problems. Pause the lecture. After you've figured out what the formal charge is on each of these, go ahead and start the lecture up again and check your answers. Okay, if we look at this first answer, the first molecule, this is what is called a methyl free radical. Now, what we need to do is count the number of electrons on it formally. 1, 2, 3 bonds, so that means 3 electrons. Now there's only a single electron on the carbon. It's not a full non-bonding pair, it's half of a non-bonding pair. So the 3 electrons from the bond plus 4 from the carbon, this actually is the same as the number of valence shells on a neutral carbon, number of valence electrons on a neutral carbon atom. So this has a formal charge of 0. And when we write the methyl free radical, we write it just like this with no charge. Okay, if we go over to this molecule, this carbon has 1, 2, 3, 4 bonds, and so 4 electrons on it formally. That will give this carbon a 0 formal charge. If I look at this carbon, however, what I have is 1, 2, 3 bonds plus 4, 5 from the non-bonding pair. That's 1 more than the valence shell, so we give that carbon a -1 charge. So this is called the acetylide anion. When we write it, we put a negative charge on that carbon. If I go over here to this carbon. If I count the electrons that are on it formally, it'll be 1, 2, 3. That's one less than the 4 that are on carbon when it's a neutral atom. So that means it has a positive 1 formal charge. So when we write this methyl, we write it with a positive 1 charge, and we actually call it a methyl carbocation. The names you don't need to know. All you really need to know at this point in time